is, well, this top row, first row, it's infinite, right? Dot 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 goes on forever. So you'd never get round to listing the second one. So that doesn't work. So what you do is you start here, and then we'll just follow the arrows. So this is the Cantor invented this technique. So you start in the top left, and then you follow the arrows, and then you add these circled rational numbers to your list. A list of what? Well, list of rational numbers. Now, notice this one here is not circled. Why is that? Well, because it's a repeat of that one. So as you're looking at each element, and as you go up the diagonal, the northeast southwest diagonal, each case. So the diagonals this way, not diagonals that way. So that way. As you're adding to your list the elements in that diagonal, before you add them to your growing list of all positive rational numbers, check that the element that you're about to add to the list has not been repeated. And if that element you're about to add is a repeat, don't add it. Okay? So that's why this one here is not circled. Circle just means that rational number is to be added to your growing list Q as you keep going up the diagonals or across the diagonals. Right? The northeast, southwest, that way, diagonals. This one is not added because it's just a repeat of that one. Its value, that value is 1, that value is 1. This one's not it's a repeat. Why is it not added? Well, because it has the same value as 2 over 1. This one. This one that has the same value as 1 over 1. This one. So it's not added. This one has the same value as 1 over 2, which is this one. So these three not added. Okay. So whenever you have a repeat in terms of value, like throw out the common factors in your So as you look at each element in your diagonal, take that rational number and divide through all the common factors that the numerator and denominator have. Have a look at the result. In other words, you've simplified it right down, and see if that result is not already included in your growing list. And if it is, then it's a repeat, so do not include it. Okay. Now, can you see just by doing this, you're not going to have any repeats. Your list Q will include all possible, because it's systematic, it covers all possible, this infinite matrix covers all possible positive rational numbers, has to, right? Because it's systematic. And then each element in that set Q is unique, right? There's only one copy, because we did not allow any repeats to be added to the list. Okay? We check each time. We check that there are no repeats. So can you see that by doing this diagonal technique, diagonalization, we now have a list of all positive rational numbers. Only one copy. There's only one copy of each element in that list, and so then we can easily pair those off with the natural numbers. Right? The first one on the list would be that one. We just pair that off with 1. The second one on the list would be 2 over 1. We pair that with 2. And the third one in your list Q, that's 1 over 2. Well, we pair that with 3. And pair that with 4, pair that with 5, pair 6, pair 7, pair 8, pair 9, and so on. Okay? We can do it. We can pair them off. We have a bijection. We have a correspondence between Q and N. Alright? Therefore, big Q, Q, is countable. Right? We've shown it. I think I've I've covered pretty well. This is just in words what I've been saying. Perhaps I should turn on the light. It's getting a little dark. If I can find my hat quickly, just a minute. I'm curious. Perhaps I should put myself in the role of a student more than I've done. There's sort of general comment. When I look at the many YouTube videos that some professor has taken in a camcorder to his lectures and got a student, I suppose, film him lecturing, then inevitably usually the professor is writing up on the board, whiteboard or chalkboard, in real time, and that's slow. So whereas there's a contrast with that kind of classroom type filming, filming of a classroom lecture, and stuff I do, whereas the videos I'm making are specifically for the internet, right? There's no class. I'm teaching to a class of 0 people. I'm just talking at a piece of plastic and metal and electronics. I'm talking to a camcorder. It's only in my head, by imagination, that I know, because I've seen it. I've seen the result many times, of course. I know that what I'm doing, what I'm saying, the filming will go all over the world because it gets onto YouTube. I know that intellectually, but emotionally, I'm just talking to a machine, right? Anyway, but that has certain advantages because it's a video. You can freeze it. You can stop it anytime you like, and so you can stop it and then read it through. You can rewind, you can listen to me again, you can stop it, you can read it through again to see if you understood it better, or if something I say is not too clear, well, you can rewind and listen to it again and again. And you can play off, you can do what? There are 3 sources of information, right? You can listen to what I say, you can read the text, you can go to the textbook. In fact, actually, when it gets pretty tight, the reasoning, what's on the board is very close to what's in the text. So you almost don't need the textbook. Pretty much. But you do need it, well, in terms of the theory, but you do need it for the exercises, because I don't solve all exercises. So you do need the text. You can get it for free on email, as I keep saying, as a general comment. Or you can get it in hard copy, paper form if you want, probably second-hand from Amazon.com. So it's your choice. All right. Well, the content here I've said in words when I was facing this way. So you have it all. All right. So. Summarizing, we have shown that Q is countable, and you may say, so what? What's the point? Well, good question. This knowledge that Q is countable, that will become a vital stepping stone to further steps in the diagonalization argument of Cantor. And then Turing later used that argument to show that the halting problem is not solvable. So it's a multi-step process, various stepping stones. So we need to know this diagonalization technique. We need to know that the set of rational numbers is, Q in other words, is diagonalizable. It's an example of diagonalization. And once we're familiar with that, we'll get onto Cantor's use of diagonalization. And then once we're familiar with that, another stepping stone, we will get familiar with Turing's use of the diagonalization argument to prove that the halting problem cannot be solved. So that's sort of the rationale behind all these stepping stones. Ciao.